I'm going to talk a little bit about the examples that is possible by the use of this silicon-based micro, maybe nano machining technologies. Basically, we have a full control over the pattern in two-dimensional case, and then we would like to stack up these patterned devices into the structure that can actually function in the way we would hope to work. So there are a number of examples and a number of real commercial examples, and I'll tell you how this basic research and basic engineering led to the real examples that we use nowadays, real serious examples. This is called inch-worm device, and what you're looking at is just, top view of the mask pattern. And as we already noticed, these square boxes with the cross, they are the anchors. These are the points where this device is actually touching on the surface, on the bottom surface. And these are the actuators, electrostatic surfaces that are facing each other. So by applying electric field, you can actually let this guy obtain the electrostatic force, or this guy obtain the electrostatic force. So the whole frame can move left and right. And also, if you look at this part, you can make the whole frame move up and down. So basically what's happening is you got two actuators, one on the left and the other on the right hand side. And you see this teeth, and the teeth can engage. So when this guy engage, when you want this guy to engage, you'll apply the electric field here in between these two conducting gaps. Then this teeth will engage, and then you use this electrostatic gap to push in this direction, for example. And in the next round, while this guy is holding this teeth, this guy will engage, okay? And this guy will disengage and then push again. So the whole operation is like engage, push, disengage, engage, push, disengage. So this cycle repeats. It's much more like how our muscle is working actually. Our muscle uses pretty much similar mechanism of engagement and disengagement. And that way you can push into certain direction, make our elastic muscle to actually elongate or contract. So you have certain amount of speed, displacement, and the forces. More than anything else, this force is really, huge force in micro scale. So this is the outcome of the result. You can make this kind of a insect-like robot to walk, using this kind of mechanism. Isn't that nice, right? What's the use of this mechanism for real commercial applications? We'll see that, So this is a real picture of this device made by deep reactive ion etching, basically. So you have a large aspect ratio. Because of that, you can apply large amount of force. Okay, so you have this engine basically, and engagement and disengagement mechanism shown here. All right. So we call this part clutch array. We call this part drive array, and we can achieve some kind of speed, 5.5 millimeter per second. That's pretty good speed actually in micro scale. If you think about the minimum feature they have is like microns. So 5 millimeters is 1,000 times of microns. So it's really fast in that sense. And the travel distance is 200 microns. That's huge if you compare with the minimum feature size. And the force amount is also 17 micronewton. That's really huge. Why do you have such kind of huge force available? Because of this engagement and disengagement mechanism. What are the problems that you can expect? Well, engagement, disengagement always requires the engagement of these teeth. And every time they do that, there will be friction force. And every time you have friction force, you will have your structure will suffer from the surface forces, which is very strong, van der Waals forces. So you will actually lose your structure because of this friction and erosion because of the friction. Okay, so you need to be careful about that. Well, this is kind of a device which is pretty similar to the one that you saw in previous slides. Well, basically, if you take a look at the detail of this part, you see there's engagement and disengagement, engagement and disengagement, right? So that way you can make this whole wheel turn into the direction you like. How can you do that? Well, there are electrostatic actuators that make this little tip move left and right and top and bottom. You have an X, Y engine separately. You see this X, Y engine, X engine and Y engine, separately. Sorry, Y engine and X engine, right? Y engine, up and down and left and right. And 4 of them will make this whole wheel turn, okay? So when this wheel turns, you need the hub, like a bearing in mechanical engineering, and the rotating structure. How can you make it? Well, we've already started, right? We've already studied, how we can actually realize such kind of a mechanism, And when this large wheel turns, it needs to actually face the surface. And if the whole surface is rubbing against the bottom, there will be a problem, friction and erosion, right? In order to avoid that, you see these little structures. What are these structures? They are the dimples. So basically, the touching occurs with this little dimple and the surface only, not the surface to surface. So this is really clever design, And it looks like it's working slowly, but if you actually make it fast, you can make as fast as you can. Because this is micro scale work, you can make it run extremely fast indeed, And extremely fast really means that you can actually operate the whole device according to the speed of electronics. And I'll talk about it later, what it really means in terms of the commercial applications. Okay? Interesting, right? And some people actually also use just the friction in order to realize certain motion, and the forces that can achieve by the certain motion could be very high because you rely on the friction itself, which is really huge force in micro scale. And what you're looking at is called scratch drive actuator. The name sounds funny, right? Scratch drive actuator. You scratch the surface and you make something move, And the structure itself is pretty simple. It has a plate and the surface and the bushing. And operation is simple and interesting. Basically, you just have a plate, lying on the surface with bushing touching the surface. And the surface is insulated. You know how you can insulate the surface? Oxidation and silicon nitride, many other things. You just apply the voltage, positive and negative. And every time you go positive or negative, whole surface is supposed to bend and touch the surface because of electrostatic force. How much is the electrostatic force? The electrostatic force is, in this case, proportional to the distance or the separation, inversely proportional to the separation squared. And how can you derive such equation and understand such phenomena, the physics, we'll cover in the other lecture, basically. So basically here, every time either you apply positive or negative voltage, they just stay still by the surface friction, okay? And that force will be huge because this gap will be nano gap, very small. You know, the electrostatic force is inversely proportional to the square of the gap size, in this case nano gap. And it is during this transition period, because transition occurs in a finite amount of time, okay? It never occurs in 0, second. It might take, 1 nanosecond, it might take a millisecond, During that transient, you see, during the transient, this guy is supposed to be released and then touch again. Whenever this guy is released, what happens is that the tip will actually move by a little distance. And that little distance will be about, nanometer range, okay? A couple of tens of nanometers, I believe, And then when it touch again, yes, it moved, okay? So every time this guy move up and down, the tip moves, forward, and every time touch again, it'll scratch and forward, scratch forward, scratch forward, scratch forward, scratch forward, okay? And that distance is amazing enough, is pretty much similar to the distance our muscle generate by the engagement and disengagement of conformational protein in our muscle. Interesting, right? So this is the one of the examples of the device. Again, what they use is surface micromachining. It's a very simple process, And what did I say about surface micromachining? It can become standard, In other words, our manufacturer just prepared the layers, what will the first layer, what will be the thickness of the first layer, what will be second, third, and so on and so forth. And this combination will be sacrificial layer and structural layer, sacrificial layer and structural layer, up to maybe 3 or 4 layers. And the patterns is all up to you, The only restriction is that many people, many groups will use the same process. So there needs to be a standard about the pattern accuracy. For instance, in many cases, the pattern accuracy is around 2 microns. So in other words, you cannot pattern anything smaller than 2 microns. If you have such patterns in your mask, they'll give you the error, or the warning at least, so that you have to change it, according to the design rules. It's called the design rules, okay? But anyways, if you use such kind of design rules and such kind of standard process, you can embed this kind of devices into any kind of structures. What are the uses of these structures? Well, there are interesting things. For instance, you can lift up shiny mirror surface. You can lift up some kind of plates using this kind of approaches. So you see, this is the plate and bushing, scratch drive actuator connected to the anchor. So this scratch drive actuator will push this anchor forward. Okay? So where is it? It's right here. Right here. This particular little thing is actually scratch drive actuator. You see? Okay? And this in red. This is scratch drive actuator. And this guy will push this direction. As it does, what we have a little thin strip of a structure. What happens to that structure? If you push it, it'll bend. What is it called? What do you call such kind of phenomena? Well, buckling. Because of buckling, it'll bend. Even though it's buckling, the whole structure is still within the plasticity limit, so it won't break, and then it'll just bend. When it bends, it'll move up, right? And when it moves up, it'll lift up this kind of structure together with it, so you can actually lift it up. Okay, so they demonstrated such kind of interesting things. You can do one more thing. For instance, like this. Well, you need a lot of forces. Then you can actually put together many scratch drive actuators together and let them push this side, let them push from this side, let them push from all four sides of this the flat structure. Okay, when it does, they consist of finger-like structures. What is it called? Hinge structures. We learned this hinge kind of structures, in my previous lecture. So when it push, the hinge structure is supposed to bend this way, and here it is supposed to bend the other way. Okay, so when it pushes, it will actually make the whole structure bend like this, and then lift up the one at the center, the one at the middle. Okay. Now what is this? This is Fresnel lens. Fresnel lens. Fresnel lens. And we already discussed. What is it? It's like the interferometric lens. Light comes through the slit, and then the cause interference of the light, and the effect is like a lens. Interesting, right? So that you can actually focus and defocus the light from the top to the bottom by making the whole thing move. So this is the operation principle. You have the top plate and the intermediate plate, and then pushing plate. Pushing plate, when it pushes through, there are hinges that is supposed to move like the other way around, so that you can lift up the one in the middle. This is operation sequence. You see, they actually push, and then they can make the whole thing lift up. In this example, it's like a little funny. This Fresnel lens actually is touching at the bottom, so that it works like a spring rather than the lens. Okay, so up to a certain limit it pushes, but when the voltage was released, it will just instantly snaps back to the surface. Snaps back to the surface. Okay, interesting, right? And you can even design a carrier that can carry the real lens. This is the polymer lens that we use in our cell phone nowadays, polymer lens. Okay, and use scratch drive actuator in XY direction, so that you can actually center and move around this lens to the point wherever you like. Basically, this opens up a way of controlling the optical image process. So at the beginning, people thought that this is highly experimental work. You see, the applied physics experimental work. But soon, the industry learned from this experimental work that they can actually realize the real application in the real field. One of the applications is mobile camera stabilizers that you use nowadays. Well, basically, mobile camera, they got lenses, right? And if your hand shakes, this lens actually is compensating for such kind of shaking by using feedback mechanism. Okay, so nowadays in your mobile phone, your device needs to use a current and a magnetic interaction. It's called VCM, voice controlled motor, to make the heavy lens move around to stabilize your image. Okay, and that causes a lot of current needs, and that is also not complete, because it's not just X and Y movement that your hands are shaking. Also, your hand may shake in theta direction then such kind of mechanism cannot compensate for it. Okay. So recently there was the MEMS startup company that came up with, actually it's not recently, this company actually has been working with this kind of group for maybe over 20 years, maybe over 30 years, and nowadays, within 5 years, they started the company, and recently, and this company actually came up with an idea that, well, people use optical light sensor. It's called CMOS light sensor. Okay, CMOS image sensor, CIS, CMOS image sensor. So instead of moving the heavy lens around, you move your CMOS sensor in the background to compensate for, the shaking in your mobile phone. And you can even make this whole CMOS rotate so that it can compensate for theta shaking as well. And that's really amazing. It requires very small amount of current. The response is much faster than voice coil motors. And as I said, you can even compensate for rotational shaking. It's basically a very innovative device. And this company is, I think, running very well nowadays, and they are trying to make these things embedded in the mobile phones, and you can check out from the website that I sent to you at this moment. Okay. So think about it. These kind of ideas came to the academic engineering world. They might publish, they might come to the journals, right? And this idea, even though it looks like an experimental thing, this idea can be implemented into commercial approach and then cause huge impact to our daily lives. Basically, you have a much better stabilizer in your mobile phone in your future. Well, there's also very interesting work that can be done by using this scratch drive actuator. This is a work done by myself, and I was at Northwestern University together with this student. Well, basically the problem was that if you use some standard fabrication, at that time it was called MCNC. Multi-user something. At North Carolina University, they actually provided the service with standard stacking of the sacrificial and the structural materials. Sacrificial, well, the silicon dioxide, right? The phosphorus PSG sacrificial, and structural materials. They are like polysilicons and silicon nitride. So if you want to use that process, you have to follow their specifications of the patterns. And pattern specification was basically 2 microns. The smallest feature you can achieve was only 2 microns, not smaller than that. The smallest gap you can achieve between these structures by the masked patterns was only 2 microns as well, not smaller than that as well. And in this particular problem, we would like to create 100 nanometer gap out of this process. It was basically impossible. If you draw such kind of masked pattern, they will reject it. Sorry, we cannot do it. That's what they say. But our idea is that, well, during the release process, it's not just the sacrificial layer that will be etched away, but also finite amount of polysilicon will be removed. We call such kind of phenomena undercut. Undercut is not good, but you cannot really avoid it, and you can use it in this case actually. So if you have certain structure, you take 2 micron of the distance and then make them approach down to 0 by using scratch drive actuator, for example. Is that 0? No. It is really the gap that can be maintained, that can be defined by this undercut. And you can achieve nanoscale gap that way. And how can you make them approach and stay there? Locking mechanism. You see that? You see? This is the mask pattern. These are the metals so that you can access these two things with the electric voltage as well. You see the spring structures, serpentine, right? And scratch drive actuators right here and right here. Now, why do we need nanoscale gap? Because we wanted to test the carbon nanotube across the gap. We have a way of fixing the carbon nanotube across the gap, and then the carbon nanotube size is really short, basically a couple of 100 nanometers. You want to place them across the gap and apply the electrostatic signals to make this scratch drive actuator move to the right hand side. You see, this is the bushing, touching the bottom, and this is the surface, so that you can actually elongate carbon nanotube and then do this mechanical testing at microscale. Use nanoscale carbon nanotubes testing at microscale to see their behavior. So, however, this gap, by the guideline of the rule, cannot be smaller than 2 microns. Okay, so this is really 2 micron design indeed. The idea is that you use, these scratch drive actuators to push and then to make this gap touch this guy. And when it does, you see right here, there's the flexible structure right here, flexible structure. This guy can, open and close flexibly. And there's this slanted structure. It's like a locking mechanism. So whenever you see this locking mechanism right here. So whenever this guy passes over this guy will open and then close, and then just lock it down. That's what he wanted. Very interesting idea, right? So this is a SAM image of the device, and let me see if we have the operation sequence right here. Okay, this is the picture under the microscope, and we applied the electrostatic signal right there, and it moved. And then touch this guy. When it touched, it pushed a little bit more, ensure that they are in touch. And this guy is on the spring, so it moves a little bit backward, right? And when this engagement is locked, well, there's a finite amount of gap. You might think that they are in touch, okay? So in order to, well, it's invisible under the microscope. We are talking about 100 nanometer gap. 100 nanometer gap you cannot really see under the microscope. So we use SEM, electrostatic scanning electron microscopy, to really figure out what happened. You see, during this course of engagement, spring right there used to be 90 degrees, right? But after engagement, you see that they actually deform, right? And form like a trapezoid, while this guy actually become, just remain 90 degrees, okay? Let me see. See? This is a picture of this guy after engagement. This gap size is exactly 100 nanometers. And 100 nanometer was maintained by the overetching or the undercut of these devices. Okay? Very interesting. Very interesting. One of the things we can think about during this whole process is that, well, actually, this gives an idea about acceleration sensing, which has already been tested and then used by this time. You see, this whole plate gives us the mass. Okay, this mass is connected to the spring. so that if you have an acceleration along the surface in any direction, the whole mass will exert force on the spring and they will deform. And by measuring such deformation, you can accurately measure the amount of acceleration. That is the accelerometers people actually develop nowadays. Of course, there are different ideas that came into the picture to make this measurement more accurate, more precise, and all kind of such engineering principles came into the picture, and that is the accelerometers that you can use in your cell phone, your mobile phones nowadays. You can go to this website, ADXL, and find out more details about it. Okay. Well, people at some company came up with many interesting ideas. You can come up with this rotating stations. You can come up with this kind of a, it's gonna rotating stations. Let me see. This kind of device that runs around the circular track. You see, these are actually scratched by lecturers, you know. And you can come up with this kind of device that runs along the straight track and movable devices. And you can lift up these optical elements, basically Fresnel lenses, and then make them move in any direction with certain rotations, so we can center all this kind of line interference together, right? And at the heart of this device is actually the use of metals to create the shiny surfaces. When you create shiny surfaces at this micro scale, you have a very good way of tuning the light or optical illuminations. And the real device that you use nowadays in projection market and digital movie cinema nowadays is actually, you know, the DLP, digital light projection technology. And in digital light projection technology, people use this kind of little patch of mirrors, which is like 8 microns by 8 microns, which is smaller, well, pretty much similar to the size of your red blood cell. And on one surface, they can arrange millions of these mirrors and then apply electrostatic forces to make them deflect. And by the deflection of the light, they can actually control or steer the light of each elements one by one. That's why people call this digital light mirrors. And you can actually cause optical illumination, you know, on over the surface. That's what people use nowadays using DLP technology. If you go to the theater and if you watch the movie, digital cinema, 100% of this cinema is actually realized by this DLP technology by the Texas Instruments. And there are even more interesting applications nowadays by this DLP technology. You know, people use this DLP chip to create optical patterns over the surface using UV light, and they use optical fluid, basically optofluid. You know, you have a liquid that can be cured by UV light into any shape that can be defined by the arrangement of these mirror patterns. You know, and that gives us very interesting possibility in biological applications and in many display applications as well. And there are many specialty market, specialty applications as well. If you go to this website, you can also find out a lot of interesting things. So you see that this kind of approaches, this kind of methods initially look like a kind of experimental approaches, kind of academic approaches, kind of demonstration of engineering principles, you know, for a conference, for a journal paper. However, this led to significant commercial applications nowadays. You know, that's how things are working. You know, from the academia, from the experiment, and from the engineering demonstrations, you can take this idea into the commercial level, and that will actually affect our lives pretty much substantially. That's very interesting process indeed, isn't it? All right, and here comes another interesting applications of this surface micromachining process. Basically, all material used here are CMOS compatible, which means that you can create a CMOS circuit, and on top of this CMOS circuit, you can create these movable devices. And the area budget of these movable devices is even smaller than the size of our circuitry. If you can see from the little chip, you can really find out these amazing structures. And this is the mechanical structure. You see there's an anchor right there, and the drive. This part is an anchor, and anchor here and here, and anchor here as well. Anchor. They are separated. There are good reasons for the separation of these anchors. You will learn from the other class of mine. And you see that these two little anchors are actually as close as to the center, rather than here. These beams actually free, suspended. You guys probably remember the reason, right? Because we would like to minimize this confinement, because this confinement will cause stress, whatever it is, tension or compression, especially compression. Compression is not good to maintain structural integrity. So you wanted to make this confinement as small as possible to avoid this structural concentration, the force concentration. And by using certain electrical feedback mechanism, in other words, you can measure the displacement of this gap and apply the current in such a way that the whole structure will go unstable. When the whole structure goes unstable, it will cause the resonance, the vibration. And because the whole structure mechanically cannot move more than certain limit, such kind of resonance becomes stable. So you can obtain stable resonance out of this unstable feedback loop. And because this is resonance, you see this is a frequency, and the magnitude of this resonance, there will be the resonance peak. And if you can use this resonance, what kind of things can you do? Well, people come up with, for example, RLC resonance circuit. And the problem with RLC resonance circuit is that oftentimes the resonance quality, in other words, quality factor, is not really good. You cannot really avoid having small quality factor. The larger the quality factor you have, the sharper the resonance peak you have. And the sharper resonance peak you have, then you can select, for example, certain kind of signal more accurately. You can steer certain kind of signal more accurately. We call this filtering mechanism, basically. And people learn that if you can implement this resonance at micro scale, first of all, resonant frequency could be, look, it's like 18 megahertz. Resonant frequency could be that of the electrical circuit, or even higher than that by using different arrangement of these flexible structures. You can even approach to 100 megahertz, even gigahertz is possible with this mechanical resonance mechanisms. And second, you can actually achieve higher quality factor than you can achieve with the electric circuit. Well, some of you might actually think about quartz resonance, which is already well used in our electronic industries. It is a standard actually. The problem with this quartz method is actually quartz is first of all huge. You need to have a certain volume budget in order to implement this quartz. Second, quartz resonance is highly affected by the temperature. Did you know that? As temperature changes, their frequency changes a lot, and that's a really big problem. Third, you have a hard time to tune the quartz resonant frequency. If you want to have different resonant frequency, you need to purchase another quartz, and that is actually very difficult for realizing this 5G mechanisms. Basically, in 5G mechanism, it's not just one frequency you want to use. You want to hop around in many different frequencies with many different electrical characteristics. Many different timing requirements are actually needed. So you want to change, you want to tune this resonant frequency a lot. With the use of this micro machine, silicon technology, you can achieve such kind of things very easily. So for example, about 15 years ago, US military started the DARPA project, DARPA, D-A-R-P-A. Defense Advanced Research Program Agency. And they pumped in a lot of money to develop silicon-based timing devices. And it was highly successful, and they came up with commercial idea. Nowadays, there's the commercial company that is on the NASDAQ, and they produce silicon-based timing devices, and they actually provide in the commercial market area. And if you go to this website, you can find out much more details about it. And of course, it wasn't easy because you need to tune and you need to be able to control this noise level down to quantum mechanical level actually. And how can you do that? By using extensive vacuum technologies, packaging technologies, and MEMS technologies and fabrication technologies. And at the heart of it is actually this multi-scale fabrication technology that's playing into the picture. Okay, you can take a look at that. So why can we actually realize this kind of a device that can process electrical circuit? This is mechanical resonators in series that provide certain kind of transfer function. Well, you can actually transform electrical signal into mechanical signal using this kind of devices. Why? Because there's one-to-one correspondence between mechanical element and electrical element. You see, this mass spring damper system can be transformed into this electrical circuit, and vice versa. You can draw your electric circuit and then realize such electrical circuit using this multi-scale, microscale, nanoscale devices actually, and that is amazing thing. So people nowadays came up with this kind of idea. If you take a look at high-speed communication devices, they have antenna, RF devices, which is ceramic and transistor electronics, crystal oscillators, filters, and many other things, VCO, mixer, electronics. Why don't we change many of these components using mechanical devices, microscale, if not microscale nowadays, nanoscale devices that can actually apply and use these high-speed electrical signals transformed into mechanical signals and then transformed back to the electrical signals. And that is really possible nowadays in the commercial market. That's what actually drives this huge innovation in your mobile and high-speed communication area nowadays. So as a result of this DARPA project, people came up with a lot of startups, and startups merged together, purchased by the big companies nowadays, and then really provide the market with the these real devices, commercial devices, and they are highly successful nowadays, I believe. Well, at this moment, I can even talk about some story about my company. This is a catalog of the company that I started. You can punch in the Google with this name and my name on it. You can easily find out about this. This little device is actually microscale thermal devices. It's a sharp needle that is made by this MEMS technology, and nanotechnology has been integrated together with that. And we were inspired by this deep brain stimulation devices. So deep brain stimulation, these sharp needles, micro needles, are actually implanted into the human brain. We implant these micro needles into plant tissues, and then we obtain the signal out of these plant tissues. What kind of signals we obtain, you can look at from our website and many of our publications. So I will show you, I will send you my publication through the KakaoTalk, that we're looking at. Well, this Wednesday, we're gonna have an exam, right? Midterm. That will be face-to-face midterm. Exam, face-to-face midterm in classroom. So the time will be same, 2 p.m. to 3:15, right? 75 exam. Basically, it's very short. And the coverage is up to today, up to the lecture. It's 17 or 18 until today. Anyways, November 9. Okay. So I've already opened the all previous lecture video clips so that you can watch it from now on. From yesterday, I believe. Today is about. And basically, remember, this is not the report exam. This is very short exam. And I cannot give you some problems that require a lot of time for you to solve. For example, I cannot ask you to come up with the detailed doping recipe to create certain kind of structures. It requires a lot of complicated job, and such kind of problems will be part of your additional report. Okay, report. They will be reported homeworks. And in this particular exam, I'd like to ask you the specific questions that has been dealt with in my class. Okay, so it will be simple questions from my class lectures. Okay, not even difficult calculations. There might be a little bit of a calculation. There might be a little bit of a request for you to draw a cross section of the process flow, but it won't be too long. Trust me. Okay. So I will give you some rooms for study. So you have a one sheet, open note. You can bring your A4 paper with everything written down and accumulated, and you can cram in as much as possible there. Okay, that will be funny. But this little paper will become your future reference. Anytime in the future, you can take a look at your paper, and then you can get your memory back. Wouldn't that be nice, right? And in this exam, you can use it. Nothing more than that. Remember, only one paper you can bring into the class and then refer to it. All right. Otherwise, if you have any other questions, you can ask me. You can ask my TA through SNS, and so we'll see you. Well, the place will be announced. Okay. So we'll see you on Wednesday. Right? Thank you. Bye.